Let's move to our second lecture objective. This is to define homeostasis and explain its significance to the function of the body. All right. Now, in order to start this discussion, I want to think about this teaser question. How does your body manage to keep your body temperature, your blood pH, your blood volume relatively constant day after day after day after day after day, indefinitely for the entirety of your existence? How does your body manage to do that? Right? That's the mind frame that we want to be in when we think about homeostasis. It's this continuous role of your body to keep all of the variables constant, even though they're being exposed to certain external changes. So how does your body manage to do that? This is homeostasis. It's the ability to maintain a relatively constant internal environment, even in the face of external changes. So some of the components that are regulated will be your body temperature, right? That's going to be maintained at about 37 degrees or so, which is your body temperature. That's what your body strives to maintain. Your blood volume. So the volumes that we just discussed earlier in terms of how your water compartments are divided, that is relatively constant. So how do we keep those proportions constant? The composition of your body, the amount of fat and protein that is sort of distributed in different areas of your body, that is also kept relatively constant. And then your blood pH, right? How do we keep these variables not exactly constant, but relatively constant in the face of external changes? And so this requires what we refer to as organ systems integration. So there are several systems playing: your muscles, your blood vessels, your nervous system, your brain. All of these various organ systems are integrating or playing together in order to bring about homeostasis. And whenever we do have a disruption of homeostasis, this is the initial basis for disease and ultimately the road that leads to death. So any disruption to the a constant internal environment is where we begin to introduce disease. A good example is your blood pressure, right? Your blood pressure is another variable that you would really need to keep consistent. The body strives to keep consistent. And if you have a disruption in blood pressure, let's say it's elevated consistently for a long duration of time, that is the basis for high blood pressure, which is a disease state, and then ultimately that can lead to strokes, etc., which leads to death. So the disruption of homeostasis is the initial step in disease and death. Now, this is an interesting visual here. This picture is a really good way to think about homeostasis. We can sometimes be tempted to think that homeostasis is the picture here on the left, where everything is perfect and in pristine condition and there's no disruption. And we sometimes tend to think that the disruption to homeostasis is what we have as disease here on the right. However, we kind of fail to think about the middle process here. The middle picture is a better explanation or description of homeostasis because our body is not always in this perfect, pristine state, right? If we run a mile, if we exercise, if we're stressed about a test coming up, we throw off some of those variables, like your blood pressure may rise if you're stressed about something. Your body temperature may rise if you're in an extremely warm climate, or drop if you're in an extremely cool climate. So we're not necessarily keeping things the same, but homeostasis is the striving to bring that back to this constant internal environment, right? Just kind of returning about your body temperature, returning your blood pressure is what homeostasis is, rather than this perfect, pristine, never disrupted picture that we see on the left. And obviously the image on the right is when we disrupt that and we start to see disease. Okay. Now, when we think about homeostasis, we want to introduce some terms that are helpful. The regulated variable, this is the aspect that is maintained. So regulated variables can be blood pressure, pH, body temperature, like we said, your acid base, which is your pH. Your body weight can be a regulated variable. your temperature. All of those are aspects that we strive to keep at a constant level, and those are your regulated variables. The set point is the value that we want to keep that variable at. So for our blood pressure, it's 130 or so over 80, okay? So that is the value that we want to keep that regulated variable at, and so that is going to be your set point. Now, in the example here, we've got our set point being 60 miles per hour, right? If you think about this car as an example of homeostasis, 60 miles per hour is the set point. Now, as you begin to climb the hill, the effect against gravity is going to naturally slow that speed down to 55 miles per hour. And that is going to trigger what we refer to as an error signal. So the error signal is raised whenever we deviate away from that set point. So because the speed has dropped, our error signal is going to increase. Now, the result of the error signal is to increase gas flow to the engine. So that's going to help to return our variable back to our desired set point by bringing about some internal change in the body. This is why several organ systems have to work together to bring that variable back to the desired set point. So in this instance, with our car, it's increasing gas flow to the engine, which is going to increase the speed. Now, when we get back to 60 miles per hour, we're going to shut off the error signal because we have arrived at our set point once again. And you can see the degree of the error signal is the degree with which we are away from the set point. So when we were at 55 miles per hour, which was really far away from 60, we had a large error signal. And as we get closer to that set point, when we're at 58 miles per hour, we see a drop in the degree of the error signal because we're getting closer to our set point. So this is just an illustration to highlight the way homeostasis works in terms of all the regulated variables. The further away the body is from those desired values, the larger the degree of the error signal. This brings us to thinking about negative feedback. So if a regulated variable decreases, the way that the system responds is to increase it. If our blood pressure, for example, drops, the change that the body will initiate is to increase blood pressure. Same thing with temperature, pH, etc. So the change is going to be self-correcting. It's going to bring us in the opposite direction of the initial move away from set point. The error signal, as we described earlier, is the difference between where we are and where set point is and where we want that desired variable to be. Let's look at another way to illustrate this, another type of example. This is with our blood glucose. So the set point for blood glucose is about 100 milligrams per deciliter. This is where we like our, at least fasting blood glucose to be. And so if you have that to start, but then you somehow, let's say you ingest a meal or you have a piece of candy or a fruit and you rise your blood glucose, you're going to trigger an error signal because now you've shifted your blood glucose away from that 100 milligrams per deciliter. Now, internally, the mechanism that will get activated is insulin. This is the purpose of insulin. It's going to help to trigger the movement of glucose from your bloodstream into your cells so that that can be utilized, and then the blood glucose level will gradually decrease. So as we shift that glucose into our cells and out of the bloodstream, we're going to see a drop in our blood glucose levels, and that is going to also drop the error signal, and it's going to help us return our blood sugar back to the set point of 100 milligrams per deciliter. So we can think of a multitude of examples to illustrate this, but the principles are the same. The set point is where we want to be. The error signal is the difference between where we want to be and where we are. And the regulated variable is the component in the body that we are trying to maintain at a set value. We also want to think about negative feedback here. Because the change was an increase in blood pressure, the way that we correct that is to drop blood glucose. And if the change, for example, let's say this has a hypoglycemic patient and they had a dip in their blood glucose, right? That can be also detrimental. The way that we're going to correct that is to release blood glucose stores into the blood in order to increase blood glucose. So the change is not always going to be increase or decrease, but it's going to be whatever is needed to bring us back to the set point, right? Whatever direction is needed. Okay. All righty, let's think about some of the components here. So the structures that we're describing here are the players that are involved in bringing about homeostasis. So the examples of those players are receptors, which detect the change, integrating centers, which communicate the desired outcome, effectors, which kind of carry out the instructions that are coming from the integrating centers in order to bring about the corrective change, and then signals are the messages that are being sent. So these are the players that are going to help us bring about those corrective changes, which are really helping us to maintain homeostasis. Now, in the example that we have here, we have a patient that's lying down or a person that's lying down, and then they automatically stand up. Now, when you stand up from a lying position, all the blood in your body tends to pool into your legs as an automatic effect of gravity. So when you do that, your blood pressure naturally falls, okay? Because your blood, especially in your core and your upper extremities and your brain, it feels like there's less blood in those organs because it's pooled into your legs. And so it feels like there's a drop in blood pressure. So that is the initial stimulus. And the way that we detect that is by a receptor or a sensor. Okay, that's how we pick up that change or that initial stimulus. Now, the way that the body is going to communicate that change in blood pressure is via neurons or sensory nerve fibers that will communicate to parts of your brain. This is where we have our integrating centers, specifically the medulla oblongata. This is one of the major integrating centers in the body or in the brain. And so the messages are sent as signals on these nerve fibers to your brain to say, hey, we have a problem. Blood pressure has dropped. You need to do something to fix this now. Okay, that's the message that's being sent to your brain. So your brain is going to take all this information and it's going to come up with the best instruction in order to correct that change. And it's going to send those instructions on motor fibers. So motor fibers are going to send some type of action or some type of instruction that will help to correct that initial drop in blood pressure. In this case, that will be to the heart. So the instruction that's sent from the brain to the heart is to increase the heart rate. And as we increase the heart rate, that is going to help to bring back up the blood pressure, okay? So notice how we have the same principles applying here. We have an initial change in a variable, which is blood pressure. We have a detection of that change via receptors or sensors. We have integrating centers, which are going to determine the best corrective change. And then we have those instructions being sent to effector organs, which is the heart in this case. And then the change that is brought about is a negative feedback because it's going to move our regulated variable in the opposite direction in order to bring it back to set point. Okay. So the principles remain the same, the players remain the same, but the variables can change depending on exactly which different parameters we're looking at. So just to reiterate the description of these players. So receptors, also called sensors, detect the stimulus. Examples of these receptors can be thermoreceptors, which detect a change in temperature. Chemoreceptors detect a change in different chemical levels like sodium, potassium. baroreceptors detect a change in pressure. So in our blood pressure example, baroreceptors would have detected a drop in blood pressure as they detect the mechanical pressure that's exerted in your blood vessels. Integrating centers are going to orchestrate the appropriate response. So this can be organs in the brain, and usually the medulla oblongata is our major integrating center. Signals. So signals are the communication or messages that are being sent. Input signals are going to be sent to the integrating centers in the brain. Output signals are going to be sent from the integrating centers out to the effector organs to bring about that change. So signals are basically chemical messages that are sent on neurons, either to the brain or from the brain, respectively. And lastly, effectors. Effectors are going to be what bring about the corrective response. So effectors can be muscles, either smooth muscles, for example, that is in your GI tract, your blood vessels. It can be striated muscle or skeletal muscle, which is your limb musculature, or it can be cardiac muscle, which is basically your heart. Or glands is another example of effectors to either increase secretions or decrease secretions, depending on what is appropriate. So these different types of effector tissues are going to help to bring about the corrective change or the corrective response. Okay. So here's another schematic, just kind of reiterating the same principles in a different way. This one is focusing more on sort of the loop effect that we have going on here. So we have a sensor detecting the change, integrating center receiving that initial response, sending those instructions to effector organs, and then the corrective response is ultimately going to shut off the stimulus, shut off that initial error signal, right? So the direction of change will be in the opposite. This is why we refer to this as a negative feedback loop, because as we shut off the error signal, we kind of make a close to the loop. So here's our sensor. Here is the change in that variable. And then here is the desired effect, which brings us back to set point. Okay. So just reiterating this, the negative feedback loop is a change that is moving in the opposite direction. The aim of the negative feedback loop is to make the deviation from set point smaller, right? Or decreasing the error signal. And then it's going to be a reverse from the change, or reverse and change from the initial value, which is bringing us back to set point. So this is a continuous process, really important as we described with that illustration. This is never done. There's always fine-tuning happening, and not just fine-tuning in the sense of making corrective changes, but also fine-tuning in the sense of detecting any changes. The body is really sensitive in always detecting any changes that could be happening and then sending the signals to make those corrective adjustments. Okay, so it's never done, always happening in the background, and that is the essence of homeostasis. Okay. Here is another example with body temperature. So very similar to what we described, we have our set point for temperature being about 37 degrees Celsius. We can be in an external environment that's really, really warm, and we begin to sweat. And the sweating is a corrective mechanism that helps us to cool the body to bring that temperature back to 37. Alternatively, we can be in an external environment that's really, really cold, right? Like it is right now in Duluth, right? So it's really cold externally, and the mechanism that would correct that is shivering. So the skeletal muscles in your body will start to contract, and that shivering is what helps to warm your internal organs and your core, and that will help to bring your body temperature back to 37 degrees Celsius. So the direction can be different depending on the change initially, the external environment, and then the desired variable, right? The desired value. All right, now we can also think about another alternative process. This is positive feedback. And positive feedback, I want to first start by saying this is much more rare in the body. Negative feedback is the much more common mechanism that we see, but this stimulates movement in the same direction as the change. It's going to amplify the movement in that direction for a short period of time for a desired result. And then ultimately, that is going to end in a negative feedback loop as well.